Section 7.4 is titled Partial Fractions, and the objective in this section is to be able to decompose a rational expression into a sum of its partial fractions. So let's begin with some background information and some motivation as to why we want to do this, and then we'll get into some example problems. Suppose that I asked you to add the fractions 1 over x minus 3 minus 1 over x minus 2. Okay, could we do that? Could we perform the addition, or in this case subtraction? I use addition loosely because we could change it to plus a negative, but could we add those two fractions together? And hopefully the answer to that question would be that yes, we could do that. We could, after a semester of studying college algebra, combine two rational expressions into one rational expression. We find a common denominator, which is x minus 3 times x minus 2. The x minus 2 denominator here will multiply across to this fraction. The x minus 3's denominator will multiply across to this fraction's numerator, and so it will be 1 times x minus 2 minus 1 times x minus 3 in the numerator. And if we combine in the numerator, we would get, let's say, x minus 2, we're going to have to distribute the negative, so minus x plus 3. If we multiply the denominator, we get x squared minus 2x minus 3x plus 6. And if we simplify everything out, we end up with 1 over x squared minus 5x plus 6. Okay, so certainly we can take two fractions and add them together and get a single fraction. And of course, had we had three fractions, we could certainly do the same sort of strategy of finding a common denominator to combine these fractions into one fraction. Now, the purpose of today's lesson is not to show you how to combine two fractions into one fraction, but to instead take a single fraction like this and break it down into its what we call partial fractions. Okay, so that'll be how the problem starts. We're going to start with one fraction similar to something like this and see if we can figure out what fractions, whether it be two or more fractions, but what fractions added or subtracted together to give this single fraction. Alright, so what's the motivation? Why would we want to write the fraction 1 over x squared minus 5x plus 6? Why would we want to write that fraction as its equivalent 1 over x minus 3 minus 1 over x minus 2? Okay, so what purpose do we achieve in doing that? How does this help us in our studies of mathematics? And the main purpose that you're going to see in your recent future, I suppose, or in your soon-to-be future of studying mathematics, is that when you get into calculus, I know there's that scary word, calculus. When you get into calculus in the next year, you're going to get into a topic in calculus called integration. Integration, the process of anti-differentiating this expression here. To anti-differentiate this expression in this form is very difficult. Okay. On the other hand, if I were to anti-differentiate the same expression in this form, this becomes very easy to do. So that's kind of the motivation. Let me throw these in here first. I know someone's going to see this and not like that those are not there, and I know you have no idea what they mean right now, and that's perfectly fine, but someone will comment, someone will say that they should be there. So let's not worry about it and move on. The idea is that we take this complicated expression here that involves higher powers of x. Oftentimes there's going to be numerator polynomials that involve x and powers of x. The idea is to take this complicated expression that is very difficult to perform this calculus operation on and change it into much simpler looking fractions so that the same operation is performed much easier. And the very difficult process of doing this and the very easy process of doing this will in the end result in the exact same answer, but the math required to turn this into this is much simpler than the math required to just do this as it is. So that's kind of the main motivation into why we're going to do and show you how to do this partial fraction decomposition. So with that said, let's get on to some problems. I have 4 example problems set up to go over with you in this particular section, and all 4 of the problems are just slightly different than each other. So, and they're really kind of the 4 types of problems that you're going to see. So I'm going to give you an example of each one. And the first one is one in which we have distinct linear factors. Distinct meaning different, linear meaning x to the first powered factors. The first step in any of these problems, kind of step number 1, is to factor the denominator. Completely factor the denominator. Okay, so I'm going to rewrite this expression in a factored form. So that becomes, I'll just write it here, x plus 7 over x minus 3 times x plus 2. Okay. Now, what we're going to do next is set this equal to, okay, so this rewritten form, we're going to set this equal to an expression that has one fraction for every factor that we see. Okay, so one fraction for every factor that we see. So in the denominator of one of these fractions goes x minus 3, and the other one goes x plus 2. Okay? Now the question is, what do we put on the top of these fractions? If we knew the answer to what goes on the top of these 2 fractions, well, we'd have the problem solved, and wouldn't that be an easy problem to do if we just knew what those were? But we don't know what those are. So for the time being, we're going to put something there. We're going to put a constant, and different texts use different constants. I'm going to use a capital A to represent the constant there. I'm going to use a capital B to represent the constant on this fraction. And so now the problem becomes, step 2 after we've got this set up is solve for the constants. Okay. Once we solve for the constants, the problem is finished. Okay, so how do we go about solving for the constants? What I'm going to do is rewrite this rational equation so that it has no fractions. So I'm going to begin by multiplying by the least common denominator. Okay, so I'm going to take this problem as it stands right now, and I'm going to multiply the entire problem by the least common denominator, and the least common denominator is x minus 3 x plus 2. So that least common denominator is distributing here, here, and here. Okay. Now, oftentimes this is just kind of a mental step in my work. I don't usually write what I just wrote in orange right there. I just kind of can mentally do it, and you will probably too with practice. But if I put this common denominator on the numerator here, it cancels these pieces with the common denominator, and it just leaves x plus 7. If I put both of these factors here on this one, it cancels the x minus 3's and it's going to leave a times x plus 2. And if I put both these pieces here, we see what will happen. It'll cancel the x plus 2's. It'll leave b times x minus 3. Okay. So now, instead of having this ugly looking complicated rational equation, we have a much simpler looking linear equation to try and solve. And the way I'm going to solve this linear equation is by arbitrarily picking some values for x. And maybe it's not so arbitrary, and there'll be a method to why I choose the numbers that I choose. I'm going to begin by letting x equal 3. I think once I do this, you'll see exactly why I'm doing this. If x equals 3 and I substitute that into the left-hand side of the equation, 3 plus 7 makes 10. If I substitute 3 in for this x right here, 3 plus 2 makes 5, so that term becomes 5a. And if I substitute 3 in for this x, well, now you see why I chose 3. 3 minus 3 makes 0, and that makes that whole term 0, which means that whole term is gone. So the equation is just 10 equals 5a, and that easily solves for a equals 2. Okay? See, I'm trying to solve for the constants. I've got one of the constants solved for now. I'm going to do the same thing by picking another number. So think about it. What other number might I choose to let x be? I can choose anything. Okay? I originally chose 3 because it was convenient to cancel this term out. So what number for x might I choose to conveniently cancel this term out? And the answer would be -2. So if x is -2, on the left side that becomes 5. On the right side it zeroes out this a term, and -2, and for this x, -2 minus 3 is -5b. That divides evenly to give me b equals -1. Okay, and then I've got the other constant that I'm after. Okay, the last thing to do after I've solved for these constants, step 3 is just to write the answer. Right? That's what we're after, is trying to find the answers, trying to find the a and the b. But I'm going to summarize this by writing out my final answer as instead of a over x minus 3, it is 2 over x minus 3. Instead of b over x plus 2, it is -1. So I'm going to put -1 over x plus 2. There's my partial fraction decomposition. And a nice little 3D box for you. Alright, the next one I want to show you that often shows up is an example that has repeated factors, repeated linear factors. So the first thing to do, again, from the last problem, the first step is to really factor this denominator out completely. So why don't I come up here and do the work to factor that denominator just to kind of save some space. The denominator, x cubed minus 4x squared plus 4x has a common factor of x. And if I factor that trinomial, it factors x minus 2, x minus 2. So we can see that that denominator has a repeated linear factor. A factor that shows up twice. Okay? Or it can show up as many times as we want, but in this case it shows up twice. So it is a repeated factor. Okay? I'm going to rewrite the problem now. Over the factorization x minus 2, x minus 2. I'm going to set that equal to. Now, just like in the last problem, I want one fraction for every factor. There are 3 factors. Even this repeated one, they're going to get their own fractions. So this one is x. This one is x minus 2. Now on this repeated one, we're not going to use x minus 2. Because if I used x minus 2, the common denominator would just be x minus 2. It wouldn't be both x minus 2. So this second one that's repeated gets x minus 2 squared. And in the numerator of each goes our constants, a, b, and c. Okay. Next, we're going to multiply everything by the least common denominator. So I'm going to multiply this entire equation by the common denominator, which is an x and x minus 2 squared. Okay, so if that distributes, again, here, it's going to go to this numerator, it's going to go to this numerator. So if I'm distributing that all the way through, what I'm going to get on the left side is just the numerator, negative x squared plus 2x plus 4. On the right side, the a, this fraction, the x's will cancel, but I'll have an x minus 2 squared. For the b, I'll get that x, and only one of these x minus 2's will cancel, so I'm going to be left with 1. And on the c, the x minus 2 squared will cancel, so we're going to get the x. Okay, so we've got this equation to solve now. And just like in the last problem, we're going to pick some values for x to cause things to cancel out, to cause terms to cancel out. So again, we're going to pick obvious, convenient choices. Let's begin with letting x be 0. If x is 0, it takes that out because of the 0 right there. That whole term goes away. If x is 0, this whole term goes away. So by letting x be 0, all that's gone. Alright, so we're going to plug 0 in for these x's on the left. I get just 4. Plug 0 right here. 0 minus 2, quantity squared is 4, so we get 4a. These terms we've already mentioned are out. They're going to be zeroed out. So that gives us a constant of a equals 1. Piece of cake. Next, we're going to let x equal 2. As putting 2 in for the x here zeros that. Putting 2 in for this x makes a 0, zeros that. It's going to leave us with just this term here. Okay, so I'm putting 2 in for the x's on this side of the equal sign. If I do that, we end up with 4. 0, 0, and I get 2c, therefore c equals 2. So I'm trying to find these constants. I've got the a, I've got the c. What I've also done, though, is I've exhausted all easy options for x. I've conveniently chosen the values for x that 0 terms out. But there's nothing left that's going to 0 anything out. The 0 did this, the 2 did the other factor, that's it. But I still have a variable to solve for. So I'm going to have to let x be something else. And here's your choice. Any number you want. Doesn't matter. Pick your favorite number, or maybe pick the easiest number that you could think of to substitute in. I'm going to choose 1, because I like 1s. They're pretty easy to work with. So x is 1. We're putting 1 in for these x's over here. If I put 1 in for these x's, the result on the left-hand side, hopefully you find it to be 5. If I put 1 in for this x, 1 minus 2 is negative 1 squares to 1, so we get 1a. If I put 1 in for these two x's right here, we're going to get negative 1b. If I put 1 in for this x here, we're going to get 1c. Now that's 3 variables, but the a and the c we already know. So I put those in. 5 equals 1 minus b plus 2 minus the 1 minus the 2 to cancel those out. We get b, or negative b equals 2, so b equals negative 2. Alright, so we now have the A and the B and the C all solved for. We can finish this by writing out our solution. The solution should be A over X, so 1 over X. Next is plus the B. The B is a negative number, so I'm going to, instead of plus, going to write minus 2 over X minus 2. Plus the C goes over the X minus 2 squared, so that's 2 over X minus 2 squared. And why not? Let's throw this nice spiffy little box there. Okay, there's our partial fraction decomposition where we have repeated linear factors. Alright, the next type of problem we're going to look at is one in which we have distinct quadratic factors. So again, distinct being different, but this time we have quadratic factors, irreducible quadratic factors. The first step is again to rewrite the problem with a factored denominator. This denominator, I can remove an x as a common factor, leaves x squared plus 4. We see that that denominator contains the quadratic because it's a sum of squares. It doesn't factor over reals. So this is what we mean by distinct quadratic factor. And just like in the last setup, we're going to get a fraction over here for each of the factors that we see. So one fraction gets an x underneath it, the other gets an x squared plus 4. Okay? Herein is going to allow or be a little difference in the setup of the problem. The linear factor x gets just a single numerical constant like we've been doing. However, the quadratic factor x squared plus 4 gets a linear numerator, bx plus c. Okay, you might remember it maybe like this, and that the numerator's degree is 1 less than the denominator's degree. So this x to the first gets just a constant, as that's an x to the 0. This x squared gets an x to the first. We want 1 degree less up in the numerator. Okay. Well, from here we're going to do a lot of the same work that we've done previous. I'm now going to multiply this entire thing by the common denominator, which is x squared plus 4. When I distribute that in, it's going to result in this. On the left hand side we get 3x squared plus 4x plus 4. On the right, the a gets multiplied by x squared plus 4, and the bx plus c gets multiplied by x. Okay. Now from here we're going to employ a different strategy than we've previously used. And so what we're going to do in this problem is we are going to work out the right side of the equation. Okay, we're going to rewrite the right side of the equation. I'm going to distribute here, giving me ax squared plus 4a. I'm going to distribute here, giving me bx squared plus cx. And now I'm going to group common terms together. I've got an a plus b that have x squared. I've got a c that has x, and I have a 4a that has neither x squared or x. Okay? And on this side, there was nothing to do here, so we're just going to keep this 3x squared plus 4x plus 4. Now the cool thing about this type of problem with these quadratic factors is now we're going to solve this problem, solve for the constants by comparing the coefficients. Okay? So, in other words, in front of the x squared here is a 3. In front of the x squared here is a plus b. Therefore, if this side equals this side, it should follow logically that a plus b equals 3. Now, in front of, let's change colors here, in front of the x is a 4, in front of the x here is a c, therefore it should follow logically that c equals 4, and that's solved for. And finally, one more to do. The constant on this side should be equal to the constant on this side. So we should get that 4a equals 4, which is divisible by 4, so a equals 1. And if a equals 1, we can come back here and say that b, if a is 1, move the 1 over, b is going to equal 2. So we've got our 3 constants solved for. The last thing to do, if you have any room at all, is to find some room and write out the final solution. I've got some space up over here, so it is a, which is 1 over x, plus, and then I need bx plus c. So the b and the c going 2x plus 4 over x squared plus 4. And there's our partial fraction decomposition. Okay, the last one to do is one in which we have repeated quadratic factors. In this particular example problem that I have set up, it is already in a completely factored state, the denominator. So I'm just going to go ahead and set this equal to 2 fractions, one for an x squared plus 2, the other for an x squared plus 2 squared. Just how we wrote the linear one when it repeated, we used it squared. Now since this is quadratic, it gets a linear factor, ax plus b. This is quadratic, it gets a linear factor, so I'm just going to keep using letters of the alphabet, cx plus d. Now we multiply everything by the common denominator. Common denominator is x squared plus 2 squared, which comes through to all these numerators, all these terms. And so the result is that on the right hand side we've got 8x cubed plus 13x. And on the left hand side we have ax plus b times an x squared plus 2. As when we put this here, only one of them will cancel, there'll be one left. Plus, and when we put this here, it's going to completely cancel, so we're just going to have cx plus d. Now, as we did in the last example, we're going to work out the right hand side of this. So I am going to, if you'd like to draw the lines, I am going to FOIL right here, giving me ax cubed plus 2ax plus bx squared plus 2b. I'm going to keep that cx and d, and I'm going to regroup things. I only have this one x cubed term. Well, I only have this one x squared term. I do have a couple of x terms. Look here, there's an x, here's an x. So I'm going to put them together as 2a plus cx. And then I have a couple of terms that lack x's, so they're my constant term. I'm going to put them in a grouping symbol, 2b plus d. And this is equal to, over here, 8x cubed plus 13x. Alright, now it's ready to start comparing coefficients. The 8 matches up with the a because they're both x cubed, so a equals 8. Now notice the b is in front of the x squared. There is no x squared over here, so b's coefficient is 0. Next I can take this 13, which is in front of the x, and match it with this term in front of the x. So 2a plus c equals 13. We already know that a is 8. So if I put 8 there, we get 16 plus c equals 13, so c equals -3. And the final one is the constant. The constant 2b plus d is equal to the constant over here, and there is no constant over on this side, so equal to 0. If b is equal to 0, that means we have 0 plus d equals 0, so d is equal to 0. Okay, so we have all 4 constants solved for. The final step is to write this solution. So I'm fitting into this form ax plus b. Remember, the b is 0, so it's just going to be 8x over x squared plus 2 plus, I have cx plus d. The d is 0. The c happens to be negative, so I probably should pull that negative out. But since I already wrote plus, I'm just going to go ahead and write negative 3x over x squared plus 2 squared. There's our last problem on the notes. Let's give it one final 3D box just for effect. And that's it.